Okay, so our second student is Gerson Leonel, who also joined us about a year ago. He did his undergraduate at Washington State University and worked with a ex-student, PhD of mine, Dee Wu, who now has a faculty position there. And his interest has been always in metal organic frameworks and polymer-derived ceramics, and he's taken over the project basically on fibers and the several samples that Gurpreet sent us. So this will be the initial results. The main goal is to understand how the different components in these composites interact. And of course, one of their forms of interaction affects their energy. So all yours.
Thank you, Alex. Good. Okay. Can everyone hear me properly? Awesome. So my name is Gerson Leonel. I am a first-year chemical engineering student at Arizona State University. I work under the direct supervision of Dr. Navrosky, and the project I'll be talking to you about today was done in collaboration with Dr. Singh. So the topic of my presentation is thermodynamic stability of polymer-derived ceramic fibers. Here's a little overview of what will be covered throughout this presentation. We'll start by talking a little bit about the applications of the different fibers and PDCs in industry. And then I'll talk a little bit about the synthesis and structural evolution of PDCs. We'll talk about the fiber samples that we have. We'll talk about their thermodynamic stability and the relationship that we observe between their microscopic and macroscopic properties. So firstly, PDCs are often employed for high temperature applications in a number of different industries, namely in the energy industry, automotive industry, and aerospace industry. In the energy industry, I believe that most of us are familiar with the way lithium-ion batteries operate. Lithium-ion batteries have anode materials that often have graphite as their main constituents. Interestingly enough, PDCs can be synthesized in a way that they have a high carbon content in the form of graphite, thus making these materials as potential alternatives as anode materials. In the automotive industry, we can see the use of PDCs, ceramic bearings, mechanical seals, and sensors. And then as we move into the aerospace industry, we can see the use of PDCs, more specifically silicon carbide composites, in turbine blades due to their high melting points or high melting temperatures. In order to understand the properties of PDCs, I believe that's important for us to understand how these materials are synthesized. So polymer-derived ceramic materials are synthesized from pre-ceramic polymers, and that's done through the pyrolysis of pre-ceramic polymers. Typically, as these pre-ceramic polymers undergo pyrolysis, we see the volatilization of low molecular weight gases such as hydrogen. And at temperatures of typically around 900, 1100 degrees centigrades, we begin seeing our pre-ceramic polymer become ceramic. So we go from a pre-ceramic polymer to a ceramic material. And the initial matrix that is formed at that temperature is more often amorphous. It's important to take note that the nature of the pre-ceramic polymer that we start with determines the microstructure and the properties of the polymer-derived ceramic material that we end up with. On the figure on the right, we have a number of different pre-ceramic polymers that are often used, such as polysiloxanes, polysiloxanes, polycarbodiamides, and so on. So, after forming this amorphous matrix, typically at temperatures of around 1300, 1500, we begin seeing the crystallization of the different nanodomains that we have in our ceramic matrix. On the figure that I show on the right, we have PDC matrix that was synthesized from a pre-ceramic polymer that contains silicon, carbon, and nitrogen. And because of that, we see silicon nitride, carbon, and silicon carbide nanodomains. So the crystallization of these different nanodomains that we have leads to the overall crystallization of our PDC material. The main takeaway from this slide is that the level of crystallinity that one can expect or will obtain from PDC is highly dependent on the synthesis temperature. Some of the common PDCs that one may have heard of or even worked with include silicon carbide, silicon oxycarbides, silicon oxycarbonitrides. I talked a little bit about nanodomains, but what exactly are nanodomains? Nanodomains, first of all, they're intrinsic to the microstructure of PDCs. These are nanophases that typically vary between 1 and 5 nanometers in size. And the different nanodomains that you may have in your ceramic matrix may or may not interact with one another. In case they do interact with one another, the interaction that exists between them may or may not be energetically favorable. And that's exactly what we assess in our study. Another interesting aspect to take into account is that in order for the different nanodomains to exist within the matrix, they must first be thermodynamically stable by themselves. So here are the 3 different industrial fiber types that we studied, namely high nickel, Tirano, and ceramic. Here's the SEM image for the 3 fiber types, and we can see that we got quite a bit of variations in the diameter of the different crystalline fibers in the high nickel, Tirano, and ceramic family of fibers. Here's the XRD analysis for the different fiber types that we have. And what we see is that we do see peaks that correspond to crystalline silicon nitride, but we do not see any peaks that correspond to graphite, which leads us to conclude that whatever carbon we have in our matrix is in the form of graphene or other amorphous sp2 hybridized carbon network. Here's the Raman surface analysis that we have for the different fibers. And we can see that in all 3 fibers, we do see the presence of this D and G bands that corresponds to more disordered carbon network and graphitic carbon, respectively. But unlike in Tirano and high nickel, in ceramic, we do not observe the presence of this G prime band. This G prime band tells us or lets us know that we have a more ordered carbon network within our PDC matrix. XPS analysis for the surface composition shows us that in all 3 fibers, we do see the presence of silicon, carbon, and oxygen. Yet in ceramic, we do see the addition of titanium, and we suspect that titanium has been used as a sintering agent during the synthesis of this fiber. Combustion analysis was used to determine the bulk composition of the 3 different fibers, and we can see that as we move from Tirano to high nickel to ceramic, the carbon content decreases, yet we see an increase in the number of bulk constituents. In Tirano, since we mainly have silicon and some excess carbon, we would expect to find silicon carbide nanodomains with some carbon, since we have a little bit of excess carbon. And then in high nickel, since we have the addition of oxygen, we'd expect to find the exact same nanodomains that we see in Tirano with the addition of silica. And then in ceramic, since we have the addition of nitrogen, we'd expect to find all the nanodomains that we see in high nickel with the addition of silicon nitride. Here are the heats of the solution that we were able to obtain through the use of high temperature drop solution colorimetry, which Alex talked about yesterday. And the heats of the solution that we're reporting here are used to calculate the enthalpies of formation of the different fibers that we have at 25 degrees Celsius. So what we're observing here is that as the amount of carbon content in our PDC matrix increases, our dissolution enthalpy becomes more exothermic. And not surprisingly, Tirano has got the dissolution enthalpy that's closest to that calculated for pure silicon carbide. I say that's not surprising because Tirano is mostly silicon carbide with some excess carbon. Here's a little bit on the details of the enthalpies of formation that we were able to obtain for all 3 fibers. On the left side, we have our enthalpies of formation from elements, namely silicon, carbon, oxygen, and nitrogen. And then on the right side, we see the enthalpies of formation from components, they're crystalline components, namely silicon carbide, silica, silicon nitride, and graphite. What we see in here is that as the number of bulk constituents increases, we see an increase in the thermodynamic stability of the fiber, which is depicted by more exothermic enthalpy of formation from elements and components. And the stabilizing effect could be attributed to the nature of mixed bonding that takes place within the interdomain region. Now, we know that we have these different nanodomains, and one of the things that we would like to do is to assess whether or not they interact with one another. And that's exactly when our enthalpies of formation from components becomes useful. The closer that number is to 0, the less interaction we see between the different nanodomains. And we can see that Tirano has a value that's close to 0, could have been closer, and errors could be attributed to errors in the compositional measurements or in the reported enthalpy of formation of silicon carbide, which was used to calculate the enthalpy of the solution of pure silicon carbide. Yet we can say that in Tirano, we have very weak or even no interaction between the different nanodomains. And it's a different story for high nickel and ceramic. I talked a little bit about mixed bonding. What exactly do I mean by mixed bonding within the interdomain region? So by mixed bonding, I mean the bond that happens where 2 or more different nanodomains come together. And mixed bonding allows for less strain, which in turn allows for more flexibility. Now, as we move to talk about the relationship between microscopic and macroscopic properties, I decided to touch bases a little bit on the Young's modulus, which is a measure of how stiff a material is, how hard it is to stretch it or to deform it. Ceramic has shown to have the lowest Young's modulus, which means it's the more stretchy, more flexible. And this flexibility that we do see in ceramic could be attributed to the nature of mixed bondings again, since ceramic is the fiber that's got the highest number of bulk constituents. In conclusion, what we observe is that we do see a direct correlation between the strain that we have between the bonds that take place in our PDC matrix and their thermodynamic stability, as less strain is consistent with greater thermodynamic stability. Ceramic has the highest number of mixed bonds, and ceramic has also got the more negative enthalpy of formation, or it's more thermodynamically stable. And from here, we're able to assess that there is a relationship between the thermodynamic stability of the fibers and structural bond strain. And this is my presentation. Thank you.